Well, thank you, and it's a great pleasure, particularly today, to be at Texas A&M. What I'm going to be doing today is giving you a talk in two parts. The first part will be a broad introduction to this effort that we have on increased oil, natural gas production, methane emissions, and climate. So you can see sort of the broad scope, the rationale, why we're doing all this work. But this work involves on the order of 50 people. And so in the second half of the talk, what I want to do is describe in a bit more detail a particular effort that we're launching as of yesterday officially with Texas A&M University. Department of Energy funding came in for it. We're going to be adding 50 more people in this broad area. And I wanted to emphasize, being here at Texas A&M, this Texas A&M effort. I'm delighted that my colleague, Dr. Erin Toulos, who got her PhD at Texas A&M, not in engineering, but in atmospheric sciences, is here with me today. And she's the lead investigator on this collaborative effort with A&M. So let me begin this talk in two parts. And I'm going to begin at a very basic level. So for many of you, this will be very straightforward at the outset, but hopefully we can go in a little bit more detail and increase your knowledge a bit as we go further and further into this. So we all know that oil and natural gas production, particularly natural gas production in the United States, is increasing. And the U.S. is now the world's leading producer of natural gas. Oil production is also increasing. And the U.S. is now the world's largest producer of oil. That oil and natural gas production is occurring as part of an energy transition that includes renewables, but also includes moving away from more carbon-intensive fossil fuels to less carbon-intensive fossil fuels. Where this is happening, I think many of you know, but it's happening in new places because of the innovations of, because of the innovations of hydraulic fracturing and horizontal drilling, but principally is occurring in places like Texas, Permian Basin, the Eagle Ford, the East Texas basins, the Marcellus, other places around the country, some of which have seen oil and gas production before. Why it's doing this. But other places have not seen oil and gas production at a significant level before. So it's a new phenomenon in many places. But principally where the activity is occurring is in our home state here in Texas. If we look at where all this increased natural gas production is occurring, it's occurring in places like the Permian Basin, the Eagle Ford, the Haynesville, East Texas Basin, as well as in Pennsylvania, New Mexico, part of the Permian Basin. So a lot of this activity in our backyard. And these transformations in U.S. Hydrocarbon supply and use have driven many different transformations. What changes the energy sector changes the world. And so these increases in U.S. hydrocarbon supply have driven large-scale elimination of coal as an energy resource in the United States, and a lot of displacement of coal-fired electricity generation with natural gas generation. So, in addition, those increases in oil production have displaced imports with multiple geopolitical consequences. And the increases in ethane and propane and butane production, so-called natural gas liquids, have transformed chemical manufacturing in the United States. The focus we've had has been on the environmental impacts on these, and we've looked at all these issues, but what I'm specifically going to be talking about, which is what's been our main focus for the last decade, which is looking at greenhouse gas emissions from these energy supply chains. So, as I stated a moment ago, much of this new U.S. natural gas production is being used in power generation. And that power generation has been the principal driver for lower CO2 emissions in the United States, replacing coal which per megawatt hour of electricity generation generates about a ton of CO2 in the United States, to natural gas, which is more than a 50% reduction of modern combined cycle facilities. So these fuel availabilities, particularly for natural gas, have driven large-scale CO2 reductions. But that's the point of those dots at the end of that slide. The power plant emissions aren't the whole story. We also need to think about the supply chains. And in particular, for the natural gas system, but also to a minor extent the coal system, but particularly the natural gas system, where the principal molecular component in natural gas is methane. If methane leaks out of this system, going from wellhead to use, then we lose some of that advantage of lower CO2 emissions from using methane as opposed to coal or other more intensive fossil fuels. So an additional concern is that methane is a potent greenhouse gas. Right? So it's not just that we could have those emissions, but they're emissions of a particularly potent greenhouse gas. I know what I've been saying so far is very basic for many of you, but perhaps here's a first surprise. All right? I'm citing a number here saying that methane is 120 times as potent as CO2. If you've heard numbers about this before, you may say, well, I thought the number was 25, or I thought it was 28, or I thought it was 32, or I thought it was 86. Yes, it is. It's also 120. All right? But let's look at how important methane is, first of all. And then we'll get to why is there this policy uncertainty. It's not scientific uncertainty. So if we compare, and this is an assessment from the Intergovernmental Panel on Climate Change, we compare the composition of the atmosphere at the start of the Industrial Revolution to the composition of the atmosphere today, and say how much warming is there due to various greenhouse gases, then CO2 is the dominant greenhouse gas. But methane is about 30% of the warming. Okay? A big fraction, comparing composition of the atmosphere today versus composition of the atmosphere at the start of the Industrial Revolution. And part of the reason for that is the potency of methane. So why do we have this difference in potency of methane? It's really a question of time scales. Okay? So the principal loss mechanism for methane that I'll use in just a moment, describe in just a moment, is the reaction in the atmosphere with the hydroxyl radical, OH. That's the dominant loss mechanism. And the current estimate of what the lifetime of this is in the atmosphere is about 12 years. Okay? So methane is referred to as a short-lived climate forcer. Okay? So if you emit a kilogram of methane today, 12 years later, you've got a half a kilogram. 12 years after that, you've got a quarter of a kilogram, and so on. You're going to get this decay. And so historically, what's been done in thinking about greenhouse gases is to integrate an impact over a 100-year period, so-called 100-year global warming potential. So imagine what you've got. Eventually, I'm not showing clearly all the reactions here, but eventually methane is going to lead to CO2. So after 100 years, all you've got is CO2. So the potency is 1 to 1. All right, but in year one, the potency is 120 to 1. You integrate over 20 years, the potency is 84 to 86. If you integrate over 100 years, it's 28 to 32. These numbers vary a little bit as the science evolves, but not that much. All right, the real question is, what's our time horizon for being concerned? And if you go 20 years ago in the climate debate, some of you aren't old enough to remember that, but 20 years ago in the climate debate, it was about, well, what is the situation going to be in 2050, in 2100? What's the warming effect going to be then? All right. And for that, 100-year global warming potential made sense. And to a certain extent, who cared about methane? Methane that you emit today won't be around in 100 years. That's changed. Right? We now recognize that climate impacts are with us today. We need things that can give us immediate impact and that we can implement rapidly. And now methane, over the last several years, has been on the top of everybody's list because the short-term impact is so large. So what have been the changes? These are, again, from the IPCC, the Intergovernmental Panel on Climate Change, 3 dominant greenhouse gases over 2 millennia. And you see the increases in concentration since the start of the Industrial Revolution. This is methane. Right? But look at the vertical scales. Carbon dioxide, current levels of carbon dioxide are about 420 parts per million. They've gone up by 50% since the start of the Industrial Revolution. N2O, nitrous oxide, has gone up by about 20%. Methane has tripled. Okay. Where's all this methane coming from? Well, let me first do an aside here. Given these potencies, how much do these methane emissions impact the warming effect of all this fuel substitution we've been doing? For example, coal, natural gas for coal. If the emissions from wellhead to use of natural gas are more than 3%, right, then we've lost all that climate advantage. If we're doing a substitution for petroleum with natural gas, doing something like having a natural gas-fired vehicle, if the emissions are greater than 1%, then we've lost all of our advantage. So the methane emissions can be extraordinarily important. And what did we know a decade ago about the emissions? Well, the emissions, nobody knew. There were no measurements a decade ago. This was a report issued by the Department of Energy and Climate Change in the United Kingdom. At that point in time, in late 2013, the UK had just imposed a moratorium on hydraulic fracturing for resources in the UK, based in part on its climate impacts. And they commissioned this report from their government to say, well, what do we know about the methane emissions? The answer came back to within the uncertainty that really determines whether natural gas is better or worse than petroleum or coal. We didn't know. No measurements. So beginning about 10 years ago, our teams at Texas and a few other places began making lots of measurements, and we used lots of different techniques. This is a member of our team going out and making a measurement directly on an oil and gas site on a pneumatic control or on a control valve that's operated pneumatically. We put and continue to put permanent field sensors out in oil and gas production regions. We did downwind sampling using a variety of different techniques. We collaborated with people who had airplanes, made aerial measurements, and increasingly we're using satellite measurements. And so we made lots and lots of measurements. I'm not going to go through the details of these. I'm going to give you the headlines. What did we find out? So remember those two numbers, 1% and 3%. Globally, and particularly in the United States, what did we think the average emission rate was of methane from wellhead to burner tip? And nationally, best number, there's argument about it, whether it's 1.8 or 2.3, but basically 2% of methane between the wellhead and the burner tip is escaping to the atmosphere. Almost all the measurements have been made in the United States. Some organizations globally have attempted to extrapolate largely US-based measurements to the rest of the world, and they, in particular the International Energy Agency, something called a methane tracker. They also estimate that this is about the situation globally. I don't know that I believe that, but I think it might be higher, but also true around the world. But the average doesn't tell the whole story. There's a lot of variability. So there's significant basin-to-basin variability. If you go out to West Texas and you had made measurements 2 years ago, that number might have come in at around 4%. If you go out the door and make a measurement in the East Texas basin, the number would be about 0.1%. A lot of basin-to-basin variability. In addition, even within a basin, I'll show you some results from the Barnett Shale in north central Texas in a little bit. From site to site, there's variability. So on the order of 2% of the sites in the Barnett Shale lead to more than 50% of the emissions. And those aren't necessarily just the bigger sites, so the sites with higher production or throughput, right? But we went through and did lots and lots of measurements. And what we found is that these measurements are highly variable, they're intermittent, they may be hard to detect, they may reoccur. It's a complex problem. And further, for the first 5 years or so of doing this, making the measurements was initially very expensive and only provided snapshots of an instant in time what the emissions were. But if we could figure this out, if we could figure out what the methane emissions are and find them and fix them, which is our mission, and to do that by 2030, how large an impact would finding and fixing methane emissions from the energy sector be? Would this be a big deal? So to understand that, we need to do what I was anticipating a moment ago, look at the balance of methane going into the atmosphere. Where does it come from? These are the sources. These are the sinks. This is the accumulation. How many chemical engineers? All right. In minus out equals accumulation, right? In, out, accumulation. Right? So in, 60% man-made, 60% anthropogenic. This is in teragrams, so think millions of metric tons, millions of tons a year. 60% anthropogenic, the remainder wetlands, termites, other things. Of the 60% that's anthropogenic, about a third is from the global energy sector and about 2/3 is from agriculture. That agriculture is principally two things. One is animals that are ruminant, so things, cows and terry fermentation. Cows releasing methane and their manure releasing methane, but then also rice agriculture leads to large amounts of methane emissions, not quite double what it is from the global energy sector. But let's just look at this, roughly 100 million metric tons a year, 100 teragrams a year of methane. If we take the potency of 80 that we were talking about earlier, right? 1 kilogram methane, 80 kilograms CO2. Take that potency, which is the 20-year time horizon, pick a bigger number. That's 8 billion tons a year of CO2 equivalent. That is the equivalent of reducing the emissions completely of all the cars in the world. That's the prize. If we can take this methane getting out, leaking from the pipe of the global energy system, we can get that to zero, all right, by 2030. That is the equivalent of taking all the greenhouse gas emissions from all the cars in the world off the road. Okay? That's the prize. Okay? Further, Organizations like the International Energy Agency say it's cheap. Right? They've estimated that half of these emission reductions could occur at zero net cost. What that means is the methane that you keep in the pipe, the product that you keep in the pipe, pays for the reduction within 2 years. Right? Many of these reductions can be done rapidly. So there are multiple organizations that have targeted zero emissions by 2030 of methane in energy supply chains. Further, global markets are demanding greener natural gas. We're going to buy your gas. Places like the European Union, Japan, Korea are beginning to say, you better be able to guarantee for us that your gas has low emissions. We're going to begin to see differentiated gas trading on global markets. So that's the problem that we work on. How do we get to zero by 2030? So I gave you a picture a little bit of where we've been. Where are we now in detecting, measuring, and mitigating these methane emissions? And there are a couple of messages here. One is that there's been a revolution in measurement technologies. So many new measurement technologies in the last 5 years, or now perhaps 5 to 7 years. But what we need to do is take all this information from new measurement technologies and combine it all, synthesize it all. So here's just some examples of the spatial scales and the temporal scales at which these new measurements operate. So there are a variety of fixed monitors that you can put right on a site, measuring continuously. Those have advantages and disadvantages. Multiple infrared imaging systems, camera-based systems, LiDAR-based systems where you can get images of plumes via a variety of different types of either drone or aircraft overflights. You can continue to go out and make measurements directly on the sites. You can fly airplanes around. You can get satellite information. A lot of new information. And so a lot of what we're doing is then combining all this information to tell us what are emissions here and here and here and here and so on. Or what are emissions globally, or what are emissions along particular supply chains. So active work going on in all of those areas, but it's a hard problem. We're doing this in multiple regions. Aaron's leading our work in the Permian. Another colleague, Arvind Ravikumar, is leading our work in the Appalachian Basin. We're collaborating with people in Colorado, with the work they're doing on basins in Wyoming, Colorado, North Dakota. We're also collaborating with people at the University of Oklahoma on work going on in the Anadarko region. So lots of places where we're making these multi-scale measurements. But to give you a visual sense of how difficult this problem remains, let me show you the synthesis of data that we had from campaigns that were done now a little while ago. This was published back in 2017, but it was done in the Barnett Shale, which is near north central Texas. So if you could collect all this information, sort of create a video of what the methane emissions are in an oil and gas basin, what would it look like? And it would look something like this. So this is the Barnett Shale region in Texas. Take hourly snapshots. These are county lines, so you get a sense of the scale. This is what you would see. Some of these emissions are normal emissions, so sort of low-level emissions throughout the basin. That's about half. The other half are these large emission rate events that are short in duration, occur in lots of different locations, variable in magnitude. So you get a satellite overpass snapshot. What does that mean? What did you just detect? You're going to compare that to continuous ground monitors. How do you do all this data synthesis? This still remains a really hard problem. And that's the problem we're working on. But what I want to do with the remainder of the time that I have is say what we're doing with A&M and these new projects that we're launching. And so what in particular we're doing is leveraging the substantial process safety expertise that exists here to mitigate greenhouse gas emissions. And so let me give you some examples. And first explain what part of the problem this helps us address. And so if you keep in mind that video that I just showed you, when we describe emissions from oil and gas supply chains, we generally break it into 4 categories. Right? One dimension is the emissions that are engineered to occur. They're intended to occur. Then there are unintended emissions. And these can be large, relatively infrequent events, or they can be small emission rate, relatively frequent events. And so all the sampling that we do tends to cover these 3 parts of the emission picture, right? Where we can certainly go out and measure those emissions that we've engineered into the system and figure out what they really are, right? Because we know where they are, we know when they're going to be occurring. Further, if we have unintended emissions that are occurring with high frequency, but relatively modest impact, low emission rates, things like a leaking valve or a flange, something like that, we can design programs where we'll go out and get enough sample in order to do that. What we won't get is the rare, relatively big events. Okay? And these, in some basins, are half of the emissions. It's believed in the United States, this quadrant accounts for, on average, a lot of variability, 40% of the total emissions. How do we get a handle on this, given how rare these are and how they can pop up? Well, what we need to do is we need to have systems that will estimate and predict what these large emission events will be. The current state of our understanding is entirely based on going out and doing, in some cases, millions of observations and trying to calculate what's the frequency of these events. And that's really not adequate, certainly to prevent them, and certainly not adequate to predict them. So what we need is a framework for characterizing, designing measurement strategies, and then mitigating these emissions. And that framework comes from the process safety literature. And these next slides were developed by Natasha and others here at Texas A&M. We've presented them multiple times before. And so we go from threats to consequences. Our consequence in this case is large unintended methane emissions. So let me show you a couple of different applications of this. So what we want to do is keep track of all the threats. They'll lead to some event. The consequence of the event is a large unintended methane emission, and we could put in preventative barriers, or we could put in mitigation measures. So let's take a really simple example. Here's a simple example of a well site. Wellhead produces liquids as well as gas, presumably goes to a separator. Separator brings out the gas, collects the liquid. Liquid goes to a tank, and you send the sales gas to the sales gas line. So what happens if, in fact, you have an event that leads to gas carryover to this tank above what it is designed to do, or a separator overpressure event, right? That will lead to a variety of different types of emissions. So what we want to do is look at those types of events, in this case, That's the middle part here, the so-called top event. We want to look at those events and we want to populate it. This might be a valve being stuck open, or it might be a sampling error in the level indicator on the separator, or it might be something called a prolonged manual liquid unloading. And so we can think about what all of these are and begin to predict when these events might happen. Right? And using this process safety expertise to predict the frequencies of large emission events, we can now begin to put in place mitigative barriers that would reduce these frequencies, rather than waiting for them to show up and then going after them, perhaps after the fact, if we can detect. And so we need data like failure probabilities that might have this characteristic bathtub shape. This is all familiar to those of you working in the process safety community. And we know that we're going to have different failure rates associated with these. We can go to the literature that exists and actually get some of these failure probabilities that have already been measured, leveraging on both industry practices as well as a large body of industry data that can allow us to begin to predict what these events might be. So now we can populate this and begin to construct fault trees to say, what are the probabilities of these? So we've done some initial exercises as we've tried to launch this collaboration, looking at various probabilities of failures that lead to an excess gas carryover to the tank. So estimating what these probabilities do, they tell us where we can most effectively put mitigation barriers or preventative barriers in place to have the largest possible effects. Until now, we haven't really had this framework in the context of the emissions. So we can predict what the occurrences per year of a certain event would be, right? And construct an entire fault tree. I'm gonna step through, I think. Yes. So the next steps here will be to construct essentially these bottom-up approaches. Now we are going to estimate things that we simply can't sample frequently enough to observe reliably. But we can develop a bottom-up approach. And so, again, I don't have results to present to you because the collaboration officially began yesterday with the arrival of the Department of Energy funding. But we can compare that to top-down approaches, collecting data on the frequencies, the magnitudes, the compositions. This is what we've already been doing at UT. So combining the expertise here at A&M with the expertise that we've had at UT and applying it to individual sites. But it's not just individual sites that we want to look at. Another thing that we want to look at, and I'll give you a slightly more detailed example here where we've developed some preliminary data, is we want to extend this framework beyond single sites. So imagine now that your failure occurs somewhere right around here in the midstream. Right, so you have a failure in the compression systems, limiting the amount of gas takeaway capacity in the production sites. Or you have an unplanned shutdown of a gas processing plant or some other phenomenon occurs here. Where are the emission consequences of that? Not at the midstream site, it's upstream. Suddenly the gas has nowhere to go. What do you do with it? And so we're also beginning to do analyses of failures of the supply chain and what the consequences of those might be. So the specific example that we've been looking at is what are the consequences of partial shutdowns of the midstream facilities? So how are we beginning to integrate top-down and bottom-up approaches to doing this. And so the disruption is now suddenly you have either increased pressure here or a shutdown of the sales gas line. Where is there opportunity for the gas to go? And in most facilities, the only place it can go is the flare. So what's the top-down data? Top-down data, in this case, is satellite data. This is a product that is from the VIRS satellite, which collects visual and infrared signatures of sources once a day globally. And what it's detecting here is light signatures from Austin, from San Antonio, from Corpus Christi, Houston's over here. And this is the Eagle Ford oil and gas production region. You can tell from the peak in the wavelength of this in the infrared of these images, what the temperature is associated with this source of electromagnetic energy and distinguish flares. So this is the Eagle Ford, and this is a snapshot of flares detected in the Eagle Ford, again, on a daily basis, using thermal imagery. So we collect all these data. We know who's flaring, when they're flaring, where they're flaring. We analyze that data. And you can ask at any given moment, what's the probability that a flare is lit? And for the most part, it's a relatively rare occurrence. These are percentages. These are numbers of flares. So most flares are lit less than 5% of the time. Very few flares are run almost continuously. So the frequencies of flaring activity at any individual flare is relatively low, with an average detection frequency using this daily detection of 11%, but a median of something like 6%. Okay, so flares are sort of relatively rare events. So you pose to yourself then the question, if flaring activity at multiple nearby sites is independent, in other words, if the failure mode at nearby sites is occurring at that site, it's independent of what's occurring at its neighbor. On the other hand, if it's part of the supply chain, it's going away from that cluster of sites, they're going to be correlated. So can we begin to look at those correlations? And I'll just show you some initial results. In the Eagle Ford, if you say at any given time, and you're looking at a single flare, at any given time, how many other flares in the Eagle Ford are lit? About 42. So we've got one flare. How many flares overall in the Eagle Ford are lit? At a 9% probability. Right? Less than 1 in 10. But what if you ask then the question, okay, I have a flare lit. What are all the other nearby flares doing? That's what this is. Within 5 kilometers, we're still thinking about how we aggregate and cluster these things. But on average, within 5 kilometers, we've got almost 4 other flares. And on average, our central flare is lit. Half of the other ones are lit. So it's clear that we're not getting just isolated events. The clusters of facilities are simultaneously having the same events. And this gives us a probability of occurrence, as well as potentially length of occurrence of these different failure modes that might lead to increased flaring. So this is an example of taking these top-down data, in this case from satellites, understanding what frequencies are. And now next steps will be coupling this with failure probabilities along the supply chains and seeing if we can begin to explain this. And so this is what this basically says. And if we looked at infrequently detected flares, that if you just look at the amount of gas flared by those flares that aren't lit very often, they account for about half of the total gas flared. And almost all of that is associated with these multi-site events. And so we're in the process of now further trying to understand and reconcile these top-down, bottom-up approaches. But I hope what this brief example is giving you is a sense of how you begin to combine all these observational data at either a single site level or multi-site supply chain level, and compare that then to what will develop collaboration with A&M on what the probabilities of these failure occurrences would be. So this won't necessarily be easy. It's not the same as taking an existing analysis off the shelf that's been done for safety and just using that information. Most of these safety analyses have had as their consequence of concern something that would lead to a safety incident. That isn't necessarily the same as something that would lead to an emission incident. So there are great opportunities to leverage existing analysis methods and data, but it's not exactly the same thing. We're going to need a variety of methods, particularly to get at this. But what I want to conclude with, though, is leaving you with, again, what the prize is. All right, so the prize is to take this, which was based on data collected now roughly a decade back in 2015. And our goal now is, this is zero by 2030. Our existing methods will get at all this base level stuff that you see. The safety approaches will get us to minimizing these spikes. And so that's where we're headed. That's our goal. And with that, I'll end and see if you have any questions.
Thank you.